there are 22 participants who are joined the PhD coursework here. I welcome all these participants in the today's session. Presentation is there. Yes. Can you see the presentation, ma'am, please? Anyone
Yes,
participate?
sir, please continue. Yes, sir, continue.
Today, friends, we are discussing about one important topic from the chemistry, that is the oxidation and reductions. Everyone is aware about this oxidation and reduction. Oxidation is a process where we change a one electron. Also in the same thing happen in the reductions. So we easily say a transfer of electron is nothing but a oxidation and reductions. In a recent research, we came that oxidation and reductions are used in a different way, like the photosynthesis, respiration, the needs of the human being, that is the batteries and the electrochemical cells. Also, we observe the such oxidation reduction type of reactions which are useful in the water treatment as well as the pollution controls. Everyone is aware about this simple definition of the oxidation. What is this one? A oxidation is nothing but a addition of oxygen, or we say gain of oxygen. We also comment as a loss of hydrogen or loss of the electrons. Here we say, look this reaction. The first reaction, where is the oxidation is takes place, in which oxygen is added. In second reaction, there is a loss of hydrogen is there, so we call as oxidation. And in third reaction, there will be a loss of electron. In first step, 2 electrons are lost to give the aldehyde from the alcohol, and in second step, another 2 electron lost to give the subsequent acid. Now, in our assigned topic of the PhD coursework, we have a reagent. The first reagent is assigned, that is from the review for the MF. That is camenophore, and everyone is aware about the camenophore, where the manganese having the oxidation state is a +7. And this is a good reagent as an oxidant. The oxidant camenophore is give oxidation in all conditions, that is acidic, neutral, as well as basic conditions. The Mn mostly used as an oxidizing agent in the form of camenophore, and second, another form, that is the MnO. What are the different applications if you came or aware about the camenophore? The basic and general application of the camenophore is there, that is the oxidation of alkyl side chain. Here we have the toluene, and this methyl is get oxidized to the respective acid. This reactions is not easily occurs. It requires 4 hours heating at a reflux condition in presence of a phase transfer catalyst. That means everyone who has learned the chemistry aware about these reactions we learn in the 12th science as well as in the SYBSc. It look like simple one, but when you are going to perform in a laboratory, it takes a time and a different catalyst in addition with a camenophore is also there. Another very good applications of camenophore, that is the synthesis of the saccharin. The camenophore is easily used as an oxidizing agent to oxidize this side chain to the respective carboxylic acid compound, and which is cyclized by dehydration to a saccharin. And everyone know the application of the saccharin in the day-to-day life. Another second application of camenophore is the oxidation of aromatic rings. When aromatic rings are present, it may be heterocyclic or non-heterocyclic. This gives breakage. But in the form of heterocyclic ring, the non-heterocyclic ring will be cleaved into a carboxylic acid group. Here, aromatic benzene from the quinoline is cleaved into the dicarboxylate. The next application of camenophore, that is the oxidation of alcohols. Everyone is aware about the oxidation of camenophore to a respective acid or aldehydes. Depending upon the reactant, which type of reactant is there, the primary alcohol or the secondary alcohol. If you have the primary alcohol, look, this is the primary alcohol. This primary alcohol is converted to an aldehyde molecule, while a secondary alcohol, which is converted to a ketone molecule. These oxidations not stop at the aldehyde level or the ketone levels. The further, as it is a strong oxidizing agent, the camenophore gives further oxidation to an respective aldehyde. Here is a very nice reactions which gives formation of an acid molecule from an aldehyde in presence of sulfuric acid. That means camenophore, when we are going to add in presence of some sulfuric acid, it gives further oxidation. We call as an excess amount of camenophore. Also, if you look, a compounds which is having the sterically hindrance, and the sterically hindered aldehydes is further oxidized to the acid molecule. In addition, with another one applications of camenophore we observe, or that is the hydroxylation process. When an alkene molecule or olefin molecules, a cyclic or non-cyclic olefins easily converted to a diol molecule. But when there is a cyclic, we say there is a formation of an cis diols are there. Or in presence of a cyclic, we say there is a syn or anti-diol formation are observed. The second oxidizing reagents we are going to review, that is a chromium 6 compound oxidant. This chromium 6 is a most abundant in 21st century from the earth crust. Everyone know the atomic number of chromium is 24. So it has a electronic configuration 3d5 4s. And this chromium, it having another two isotopes, that is chromium 53 and chromium 54. But out of that, the chromium 52 naturally it is abundant in nature, so it is possess two oxidation states, majorly, or we say commonly, +3 and +6 oxidation state. The wide oxidative reagents consist of chromium 6. The first oxidative reagent is a chromic oxide oxidation in presence of a sulfuric acid. When you add a CrO3 in presence of a sulfuric acid, we refer as a Jones reagent. And when, in addition with that, if you oxidized alcohol in presence of an acetone reagent, then it is known as a Jones oxidation. Sometimes the peoples are jumble in a Jones reagent and Jones oxidation. But when you use a acetone as a reagent, then we call as a Jones oxidation, and sulfuric acids then known as a Jones reagent. These are the examples of Jones reagent. We observe the three different reactions I have shown here. If you look for the first reaction, what is the first reaction? In the first reaction, we observe that there will be a primary alcohol as a reagent. In secondary, also there is a primary alcohol as a. The reaction condition are different. When you perform reaction at a 0 degree Celsius, we observe there is a formation of an aldehyde. But if you increase somewhat temperature to a room temperature, the oxidation of alcohol is not stop at the aldehyde stage, it is further converted to the acid state. That means at room temperature, by changing the or varying the conditions, we get a different product. In the second, here we have the secondary alcohols. And when you are perform oxidation of secondary alcohol, the secondary alcohol give the formation of respective ketone molecules. The second reagent from the pyridine, in which we use the chromium, we call as a PCC reagent, pyridinium chlorochromate. This pyridinium chlorochromate, when easily prepared from chromic acid, if you add some amount of hydrochloric acids, we get the pyridinium chlorochromate. And the major application of PCC are the primary and secondary alcohol oxidations. The primary alcohol are oxidized to aldehyde, and ketones are oxidized. Ketones are formed from the secondary alcohol. Look the different example. This is the general reactions where the oxidation takes place. The alcohol is converted to the aldehyde. Which definition we used here, or which definitions we can imply for this oxidation? We say there is a simple removal of hydrogen. Here H2 is removed, so we called as an oxidation. The alcohols, here is the primary alcohol. The primary alcohol are converted to the aldehyde. And here if you look, there is a alcohol which is also a primary one, is again converted to the aldehyde. But in the third example, this is the alcohol which is present in the position we label or we call as a secondary alcohol. And this secondary alcohol is converted to the ketone molecules. This is the importance of the PCC. Primary is converted to aldehyde and secondary is converted to the ketone molecules. Also, it gives oxidation of the allylic alcohol, because sometimes there is a allylic alcohols and these allylic alcohols are present. And here we have an allylic alcohol, and the carbon where it is present, it is a tertiary carbon. And when tertiary allylic alcohol are present, they will be rearranged. The rearrangement process will be takes place, and we get the formation of an this alpha and beta unsaturated ketone molecules. How the rearrangement is takes place? Everyone know about the sigma-tropic rearrangement. 3-3 sigma-tropic type of rearrangement. This converted in by means of an intermediate allylic chromate ester. Another one example, if you look also, this example implies a allylic tertiary alcohol. This allylic tertiary alcohol is also rearranged to a alpha beta unsaturated ketone molecule. Okay. Now the next reagent is the cerate oxidation, in which we also use a chromium as an oxidizing agent. The cerate reagent is formed from the pyridine and the CrO3. This having the same oxidation like your PCC, conversion of primary to the aldehyde and secondary alcohol to a ketone molecules. But important, why this reagent having the importance? It is a acid sensitive group, and as it is a acid sensitive, the other oxidizable groups does not change. They will be remain unaffected. So this gives a easily conversion or easily oxidation of a less oxidizable groups are also. But there is a disadvantages, that is the removal of this serrate reagent require excess amount of the pyridine after the reaction is over or a reaction get completed. This is the first conversion where we observe that there are two hydroxy groups. One is a secondary alcohol and one is a tertiary alcohol. And out of this secondary and tertiary alcohol, only the secondary alcohol get oxidized, while the tertiary will be remain unaffected. This is the key features of the serrate oxidation. Second example, this is a simple single primary alcohols. So it will be converted to the aldehyde molecule. Another importance is that here is a allylic position, there is a epoxidation which takes place. Epoxide is present in the reactant molecule, which is oxidizable. But this oxidizable epoxide remains unchanged, while this primary alcohol is converted to an aldehyde molecule. In the next example, we observe that there is the protections, diol protections are there. This diol protection remains unaffected, that is ketonic molecules, while the secondary alcohol get oxidized to a ketone molecule. And in the fourth example, we observe that again there is a primary alcohol. This primary alcohol is oxidized to an aldehyde, while remaining this nitrogen bonds unaffected. This is the key features of the serrate oxidation. That is, oxidation takes place, but due to the acid sensitive group, the other functional groups are remain unaffected. The third, another chromium where the is used in presence of an DCM as an solvent, dichloromethyl, CrO3 pyridine. But here is a DCM is there, and this they will be added in the 1:2 quantity. We called as a Coulin's reagent, or also known as a Coulin's-Radcliffe oxidation. It gives a primary alcohol and secondary alcohol to the respective aldehyde and ketones. The key features of these reagents is the mild reaction condition without affecting the other functional group, but also similar with this serrate reagent, it also having the one disadvantage, that is the excess use of the reagent is required. So we move to another one, a good oxidizing reagents and very selective reagents, that is pyridinium dichromate, known as a shortly PDC. This PDC is oxidized in presence of the neutral condition. Secondly, the excellent yield will be observed to convert primary alcohol. In the first example, if you look, this is the primary alcohol. This primary alcohol is oxidized to an aldehyde. While if you look the second example, in the second example, there is a secondary alcohol and tertiary alcohols. This secondary and tertiary alcohol both are allylic alcohols. And these allylic alcohol are rearranged or oxidized to an alpha beta unsaturated carbonyl compound. But again, this condition is there without affecting other functional group. That means secondary alcohol are oxidized easily as compared to the tertiary alcohols. Here in the third example, this lactone remain as it is. No change will be present on a lactone while converting this primary alcohol to the aldehyde. The sterically hindered compounds we observe in this fourth reaction, where the alcohols different alcohols are present. This alcohol bears here on a carbon is a tertiary one. This is also a tertiary one. Also, we have a lactone ring. That means three different oxidative groups. Additionally, there is one epoxide also there. All these remains intact. Only the oxidation of this secondary alcohol takes place to a ketone molecule. In the third, we observe that if we use a trimethylsilyl peroxide and the PDC reagent, the secondary alcohols converted to the ketone molecule. That means only reaction does not take place in presence of DCM. Also, you can use the trimethylsilyl peroxide to show the conversion or to give the new oxidized aldehyde or ketone molecule. This PDC also oxidize a alkene molecules where a carbon-carbon double bonds are present, and this alkene molecule are converted to a respective alpha beta unsaturated ketones. This is the important applications in the synthesis of the unsaturated compounds. All these examples, say first and second example, gives a formation of a alpha beta unsaturated ketone. And when you look for the third example, it does not convert it or unable to convert into the alpha beta unsaturated ketone, as there is a no allylic carbon atom where the oxidation takes place. And in such cases, the CrO3 in presence of acetic anhydride gives formation of an epoxide. Hence, we say the alkene are converted to alpha beta unsaturated ketones or alkene are converted to the epoxide. This CrO3 in presence of acetic anhydride, like KMnO4, also give the oxidation of an allylic side chains. Here is the allylic side chain present with methyl group, that is the para-nitrotoluene. This converted to an aldehyde. The first acetic anhydride takes part to convert into the respective ether molecules, and then on hydrolysis it converted to the aldehyde molecule. Second reactions where the promyl chloride methyl group which converted to the aldehyde. We are discussing next in detail about this Sorin oxidation. The third example where there is a xylene molecule. In the xylene, there are the two allylic side chain atoms, and due to the presence of two allylic side chain atoms, when you reflux in presence of chromate compound or chromium compound, they converted into the dicarboxylic acid, that is the terphthalic acids, where a one methyl group also oxidized to the one functional group conversion or one side chain oxidation. This CrO3 also gives the oxidation of aromatic ring. The KMnO4 break the side chain aromatic, while the CrO3 gives partial oxidation. And due to partial oxidation, the aromatic ring is converted to the compound like a quinone molecule. Here the quinone type of oxidation takes place in a ring where there is a substituent are present more, that indicates the substituted aromatic compounds partially oxidized as compared to the non-substituted aromatic compound. Second, here anthracene is converted to the anthraquinone by using the CrO3 in presence of an acetic acid. The another one application of the catalyst, that is the chromium 6 in a chiral as an chiral oxidation. the chromium takes place a good oxidative reagents as an chiral to form an epoxidation. When you have the trans-alkyl, the important conditions, that is the trans-alkyl. Here is the trans-alkyl. This trans-alkyl get epoxidized in presence of the chromium 6 catalyst. These reactions takes place by means of catalytic or stoichiometric mode, but the stoichiometric mode is slightly well as compared to the catalytic mode. Here is the catalyst used for chromium 6 catalyst is for the conversion of this trans alkene to an epoxidation. This reaction is known as a asymmetric epoxidation. Now, we use a cheminophore and chromium for oxidation. It has some limitations, as well as we have to care about the toxicity when we performing the reactions or handling the cheminophore. The limitations of cheminophore, like it's having a strong oxidizing nature. So it can oxidize a different substrate, and due to that, there is a less selectivity observed in the synthesis. Also, some natural organic compounds which are rapidly consume the cheminophore, and due to that, the efficiency in a water treatment is get reduced. So we say it is sensitive to the organic matter, hence it is less efficient in the water treatment. Also, we have one good applications, but where there is a MnO2 is produced from the cheminophore, and due to this maximum amount of cheminophore reduced, we are unable to decompose, or we have to further treat to convert into the green methods. We also have a limitation like a corrosions to damage the equipments. Also, some reactions efficiency is observed as an less one. The cheminophore is not too much toxic in nature, but we observe the burning of the skin, eye, or place also to the mucous membrane. Hence, we have to take care when we are performing reactions with a cheminophore. Also, it is hazardous when get inhaled in the form of aerosols. It can cause a respiratory irritations. It damage to the aquatic animals, harmful to the mostly aquatic animal, that is the fish, and it maybe gives some neurological problems because in cheminophore there is a magnesium is present. If you look for the chromium, hexavalent chromium, it is also a highly toxic in nature actually. So we have to carefully handling and dispose. We have to also perform a careful disposal. It is carcinogenic in nature, and this hexavalent chromium it is reduced to the chromium 3. Hence, it is not stable. So the reducing environment give the change in the its efficiency. So another one limitation for the chromium 6 is when you use in a water treatment, there is a formation of the complex precipitation takes place. So we cannot use the chromium 6 directly in a water treatment. It is toxic in nature, so we have to take care when you are performing the reaction, as it is carcinogenic in nature. Also, it damage to the DNA. It increase the risk of the groundwater contamination as it is highly soluble in a mobile water, and hazardous when inhaled. Mostly, it gives asthma or the lung damage. This is the about classical review of the chromium and Mn molecules. Now we look at some oxidating reagents which are used or which are focused majorly by the researcher to convert selectively to an aldehyde and ketones. The first name will become that is the Sorn oxidation. The Sorn oxidation specifically gives conversion of primary alcohol to an aldehyde and ketone in presence of the oxalyl chloride. Oxalyl chloride COCl2 twice. The reaction takes place in presence of an DMSO and basic nature or base reagent, that is the trimethyl amines. When you used a primary alcohol, this primary alcohol easily converted to the aldehyde molecules and secondary alcohol are converted to the ketone molecules by using this Sorn oxidation of oxalyl chloride in presence of DMSO and a basic condition or basic nature. In this second example, we observe that we have the two primary alcohols. Two primary alcohols are the different one. How they are different in natures? This primary alcohol is present on a tertiary carbon, while this primary alcohol is an allylic carbonate. By this, both are get oxidized to an aldehyde without affecting a other functional group or other oxidative group reagents. So Sorn oxidation is a good alcohol into an attacked by this electron halogens, and these halogens again intramolecularly or say by means of intact ion pair, it attack on the sulfur, gives a formation of an intermediate sulfonyl compounds. The primary alcohol is treated with this sulfur halogenated compounds, and in the next step, the basic reagent triethylamines, it abstract the protons, form an carbanion, and this carbanion rearrange this intermediate to give the formation of an carbonyl compound with a removal of dimethyl sulfide. This is a simple mechanistic way in which there is a removal of carbon dioxide, carbon monoxide, and a chloride molecule or chloride ion, not a molecule, chloride ion. This Sorn oxidations, as stated for earlier, it converts primary alcohol to an aldehyde without affecting other oxidative functional groups. When we are going to perform a reaction on a both type of alcohols, primary alcohol as well as secondary alcohol, this chromyl chloride gives oxidation of both the primary alcohol to an aldehyde molecule and secondary alcohol to an ketone molecule. They both will be converted into its oxidized state. We look here another one example where there is a protecting group is present and two different protections are there, one for the hydroxy group and one for the ketonic functional group. This remains as it is. There is no affected on the protecting group, and this chromyl chloride gives oxidation of primary alcohol to an aldehyde molecule. Here is a cyclic, not a cyclic one, but it is just a primary alcohol. This primary alcohol is again oxidized to an aldehyde molecule. This is the called as Sorn oxidation by using chromyl chloride in presence of DMSO and triethyl amines as an base. The next oxidizing reagent you have to aware, that is the Des-Martin period name. In short, we known as a DMP reagent. This DMP reagent is a iodine compound which is present in a hypervalent state. The Daniel Benjamin Des and James Martin prepared the reagent from the orthoiodobenzoic acid. This hexavalent iodine, when treated with a potassium bromide and further acylation carried out by using the acetic anhydride, give a formation of the DMP. This is a very selective oxidizing agent which gives oxidation under a neutral conditions. We have a oxidation of an different alcohols to a respective aldehyde and ketone. But important, it is a selective oxidizing agent. This is a hypervalent iodine compound known as a DMP. The different applications of the DMP, if you look, we have a neutral condition, or we say nearly neutral condition. In that condition, we convert this primary alcohol to an aldehyde molecule. While if you look another one, this is the selective oxidations of the alcohol which takes place, again primary alcohol to a aldehyde functional group without affecting other oxidative functional group. The second, third one is also the primary alcohol converted and a aldehyde functional group. Now look, some research article published in which this Des-Martin reagent are used. This is the secondary alcohol, and the secondary alcohol is converted to the ketone. The article published in Journal of American Chemical Society in 1992, where Des-Martin reagent used for the oxidation. Another one article published in the same journal in the same year, where we have two different alcohols are there. One is a primary alcohol and one is a secondary alcohol. But selectively, the primary alcohol oxidized to an aldehyde, while the secondary alcohol is remain intact. There is no oxidations or the conversion into a ketone molecule. Hence, it is a good selective mild reagent for the sensitive functional groups. And another one, precursors, where the reactions occurs at a room temperature. Look, another some articles in which Des-Martin are used as an oxidative for the oxidation. In 2004, the secondary alcohol is converted to the ketone molecule. This is actually a bicyclic ring where the side chain part is oxidized to the ketone, and published in 2004. Another one, conversion of secondary alcohol to a ketone by using a Des-Martin, published in 1993. And primary alcohol conversion using a Des-Martin is published here in 2002, where we got the formation of an aldehyde molecule is takes place. Yes, we have to move for another next reagent. I think from 45 minutes we are talking. All are audibles? Yes?
Yes, sir. Please continue.
Okay, no problem. Another one very good oxidative reagent is a tempo. What is the tempo? This tempo is a 2, 2 and 6, 6 tetramethyl piperidine 1 oxalyl. Actually, it is an oxygen radical. This oxygen consists of one electron, we call as oxygen radical. In 1960, first it is prepared by the two scientists, that is the Lebdev and Kramanovsky. This tempo is used for the selective oxidations. And when we are performing this tempo, sometimes NaOCl, sodium oxychloride, is used as a co-oxidant. And this co-oxidant reagent, used as a catalyst, it gives good conversion to a respective aldehyde and ketones. Now look the first reactions. In the first reaction, the simple single, that is a primary alcohol is present, and this primary alcohol is converted to an aldehyde. But when you move to the second example, where multiple alcohols are present, we have primary alcohol, we have two secondary alcohols are there. And also the oxidative group like a ester group, then imine groups are there. But out of this, only the primary alcohol is oxidized to an aldehyde molecules, while the secondary alcohols, esters, and these imines will be remain as it is. Hence, we call as a selective oxidizing reagent. Now look these articles where the tempo is used as an used for the oxidation purpose. This is the long chain cyclic molecule. Primary alcohol is oxidized by using the polystyrene based oxidant and tempo in presence of acetone to an aldehyde molecule, published in the Synthesis 2003. In 1999, this tempo is used for the oxidation of an benzylic alcohol. This is the benzylic alcohol. This benzylic alcohol, in presence of trichloroisocyanuric acid, gives formation of an aldehyde. That means you can easily prepare aromatic aldehyde and ketones from a benzylic alcohol using a tempo as an oxidative reagents. With all this number of oxidating agents, another one oxidizing agent will be more focused by the researcher, and that is the oxane molecules. Actually, oxane is used in a form of its dialkyl molecule, so we call it as a dioxidant. This dioxidant molecule is a versatile oxidizing agent used in a convergence of a ketone molecule or alkene molecules. The ketone molecules in presence of oxane give the oxidants, while alkene molecules give the formation of the epoxide molecules after breakage of this oxidant rings. When we have the ketone molecules, and this ketone molecule are chiral in the nature, we use a chiral dioxirane for the conversion of alkene into the epoxide. Look, this is the ketone molecules, and this ketone molecule, by using a oxane molecule, converted to the dioxirane, and this dioxirane, when we treat with the alkene molecule, this alkene molecule give the formation of the epoxide. Okay. That means here is the cis alkene molecule is created to give the formation of 91% enantiomeric excess and 87% yield to convert into the epoxide molecule. Earlier, we learned about the trans epoxidation by using the CrO3 to give the epoxide. These are the different oxidizing agents which are prescribed in your syllabus. We will go thoroughly to learn about its applications, majorly in the research and general applications in day-to-day life. Now, we move toward the second topic, that is the reduction. Everyone is aware about the reduction is just opposite of that of the oxygen. Reduction is takes place when there is a gain of electrons. We observe in this third reaction, we have the two butanol, and when the two electrons are gained, it converted to the two butanol. Or we say there is a loss of oxygen atom. In the second example, we observe here, there is acid. After loss of oxygen, it gives a aldehyde molecule. Or we can say a addition of hydrogen. In an aldehyde molecule, if you add an hydrogen, they it get reduced to an alcohol molecule. These are the simple definitions. We can use mostly one definition will be implies one times or more than one definition also implies to the convergence. The majorly used reducing reagents are the lithium aluminum hydrides. The lithium, everyone is aware about the lithium aluminum hydride is a very powerful hydride donor. And so it is violently react in presence of an water or a protic solvent. So we have to care. We does not have to apply the water or protic solvent. Rather than that, we can use a dry ether or use a THM or the dioxin or protic solvents. So the lithium aluminum hydride gives reduction of different functional groups. Majorly, we observe that the aldehyde, ketone, ester, carboxylic acid, anhydrides, acyl halides, epoxide, all they are reduced by using a lithium aluminum hydride. The lithium aluminum hydride prepared by a simple conversion using a dry ether as an solvent. Lithium hydride treated with aluminum chloride. This gives a formation of the lithium aluminum hydride. The paste type of compound we observe. The lithium aluminum hydride have the wide applications. Mostly we look in a pharmaceutical synthesis, different intermediate of the pharmaceuticals are synthesized using a reducing reagent. In the natural product synthesis, also stereoselective reductions are also observed. And the simple, mostly in the research, we used to reduce a carbonyl compound to convert or to synthesize a bioactive or biopharmaceutical molecules. Different polymers, they are prepared by using a reduction using a lithium aluminum hydride. A simple applications like a surface functionalization, a maximum times in the synthesis of nanomaterial synthesis like a mono nanomer, that is the one metal is used in the synthesis like that. Mostly research takes place on titanium oxide as a nanomaterial. It also used in a nanomaterial where there is a metals are there. Also, the lithium aluminum hydride used in a energy research, hydrogen storage research, as well as inorganic chemistry applications. I have not given the different examples for the reductions. I just have summarized some applicative part of the lithium aluminum hydride. Now we move to a second reducing reagent, that is the sodium borohydride, NaBH4. The NaBH4 is having the similar reactivity with the lithium aluminum hydride, but importance is that it is a selectively. It does not reduce all the carbonyl functional groups, but only reduce to the aldehyde and ketone to the respective alcohol molecule. The group different carbonyl groups like carboxylic acid, esters, epoxides, or lactones, they remains unaffected. The compounds which possess halogens, cyanides, amide, and nitro compounds, they are reduced by using the lithium aluminum hydride. But when you use the sodium borohydride, it does not convert into its reduced form. It will be remain unaffected. Hence, we say it is very selective reagent, but as compared to lithium aluminum hydride, it has the less reactivity. We prepare sodium borohydride from a sodium hydride with the trimethyl borate at 250 degrees Celsius. At this high temperature, it converted to the sodium borohydride. Here are some examples of the conversions of the major functional group like aldehyde to alcohol, ketone to secondary alcohol. Again here ketone to the secondary alcohol, but ester functional group remain intact. Second, third, fourth example, again we have the ketone and ester two functional group. Sodium borohydride only reduce the ketone functional group, while the ester will remain intact. Also, it is applied for the reduction of alpha beta unsaturated compounds, where this carbon-carbon double bond is remain as it is. It does not further reduce. Only the carbonyl functional group is reduced, and we get a formation of a alcohol, primary alcohol from the aldehyde, while from the ketone we get a secondary alcohols. This is the application of lithium aluminum or sodium borohydride. In a similar to the sodium borohydride, lithium borohydride also give the selective reductions, but it is somewhat more reactive as compared to the sodium borohydride, but less as compared to lithium aluminum hydride. The another one reagent which is used selectively, that is the DIBA, diisobutyl aluminum hydride. The two aluminum atoms are present in this DIBA, hanged in between a isobutyl atoms and hydride. This is a electrophilic reducing agent and colorless compound. We treat DIBAL in presence of a solvent like toluene and hexane. The DIBAL is prepared by using the triisobutyl aluminum. Its dimer is formed from addition of just a hydride. The DIBAL having the different applications. Selective reduce the ester molecule, nitrile molecule, amide and amide molecules. The ester, nitrile and amides all are converted to a aldehyde functional. That means selectively we have to reduce an aldehyde ester molecule, but we have to remain another aldehyde molecule intact or ketone molecule intact. We use a DIBAL as a reducing reagent. Ester is converted to the aldehyde. Also the cyanide, here we have given an example. This is isonitrile. By using a DIBAL, we get the formation of an acetaldehyde. Second, this is further, if you use in the form of excess amount, like a oxidation, in a oxidation, reverse to the oxidation, in excess amount, this ester is not reduced to the only aldehyde, it further get reduced to a alcohol molecule. That means in a catalytic amount, DIBAL gives the aldehyde, while in an excess amount, it reduces to a into alcohol. These are the applications of the DIBAL. And another one, a very good applications of the reducing reagent, that is the dissolving metal reagents. The dissolving metal reagents Actually, these are the gives partial reduction of the organic molecule by means of a single electron transfer mechanism. The reagents like metal, sodium, lithium, or potassium in presence of liquid ammonia or tertiary butanol or the methanol gives a reductions or gives a single electron transfer mechanism to reduce a partially aromatic ring. A famous reduction everyone know, that is the Birch reduction, where the 1,4-cyclohexadiene is formed. Depending upon the electron donating and electron withdrawing group, there is a 1,4 or 1,5 isomers are formed. The alkyne is converted to the transalkene. Specifically, everyone knows to perform by using a metal. Then we observe a reduction takes place to the alkane molecule. But if we have to stop the reaction at the alkene stage, the catalytic amount of this dissolving metal used to get the transalkene. The heterocycles also reduce. This dissolving metal are used for the breakage or cleavage of the aryl oxygen or aryl sulfur bond. Also, the conjugated enones are reduced by using the such type of dissolving metal reagents. These are the some reducing reagents we used for the reduction. Also, we have the superhydride molecules. The superhydride triethyl lithium boron hydrides molecules. These are very powerful. We say extremely powerful and selective hydride reducing reagent. All are Dival lithium aluminum.
Sir, your voice is not coming. Participants, please wait.
Yes.
Sir
Now
has
audible?
joined. Yes,
Yeah.
sir. Please continue.
Okay. I have to explain the last slide.
Okay, okay.
Yeah. Now, the superhydride, these are the very powerful and selective reducing reagents. Wide applications are studied by using the superhydride. Generally, observed that is the reduction of carboxylic acid derivatives. The ester converted to primary alcohol, acid halide, mostly chlorides are converted into the primary or secondary alcohol depending upon the position of halides. Lactones converted to the diols, amide, which is converted to the amines. Similar, same thing, amide are reduced by using the lithium hydride, lithium aluminum hydride, but more effectively, the superhydrides use conversion. Nitriles converted to its primary amine. These are the majorly focus areas of the researcher. And also, the superhydride are used for the conversion or reduction of the carbonyl compound, enone compound, diketone compound, organometallic precursors are converted by using the superhydride. Removal of the oxygen, that is called as a deoxygenation process, and reduction of the halide also takes place by using the superhydride molecule. These are the some oxidation and reducing reagents. I just have to summarize. I apologize for the reduction for the for that where I doesn't put the too much reactions or unable to add the new recent research articles. Uh, at the last, I'm very thankful for the Dr. Jagdare sir and Dr. Adoy sir for inviting me in this coursework. Thank you very much. Now, I request the participant if you have any questions about this, kindly share. Okay.
Thank you, sir, for explaining the concepts of oxidizing and reducing agents so clearly. Your explanation will greatly help us understand redox reactions and their applications in chemistry. So, all participants are requested to ask questions. If you have any doubt regarding this lecture, raise your hand or you can put on the chat box. Please put your doubts on the chat box. Participants are requested to ask their doubts. If anyone is having any doubt, they can put on the chat box simply.
I think there is no question. That means
They have
all
understood all the
participants
concepts clearly. Yes, sir.
understand very well, or there may be
Yes, sir.
possibility they doesn't understand
Yes.
anything. Okay, no matter.
So,
Here I am going to
mm,
share my presentation with advisor for preparation to this all participant. Those are
okay.
unable to, that doesn't get the clear files. I also share this presentation with them. No matter. Thank you.
Thank you very much, sir. And I express my heartfelt gratitude to you and our honorable principal, Dr. B.S. Coordinator Dr. T.B. Pawar sir, and all the faculty members and research scholars